Let's talk about phase change diagrams. So we've been talking before about phase changes in general. So like what are um, phase changes? So it's converting between different phases of matter. So for example, melting and freezing, boiling, vaporization, condensing, sublimation, deposition are all phase changes. Um, and we talked about why phases change. And that it's a combination of the repelling forces of kinetic energy and the attractive forces of pressure and electrostatic interactions. So there's a way to summarize all of this information for each particular um, uh, substance, chemical substance of any sort. And it's called the phase change diagram. And every substance has a different phase change diagram. And what the phase change diagram does, I'll zoom in just a little bit so you can see that a bit better, is it shows you what phase of matter that substance is at particular temperatures and pressures. So taking a look at this diagram, this is for water. The x-axis is temperature and the y-axis is pressure. So when you're reading this, you have to know the x and the y-axis. And then there's kind of zones. Let me grab some colors that might kind of help us here. Let's see what would be a good color. Let's do blue for solid, and maybe we'll do red for gas, and we'll do like a purple for liquids because they're kind of in between. Okay, so here's the general rule. We have these three different lines on this graph. So let's think about this logically for a second. If we are at low temperatures and low pressure, or low temperatures and very high pressures, what would we expect the state of matter to be? Well, temperature is a force that it's a repelling force. If it's lower, it's less likely to be a gas. Pressure pushes things together and makes them solid. So in fact, this whole zone of the graph, kind of highlight that whole zone is solid. Okay, so at low temperatures and high pressures, water tends to be a solid. It turns into ice. That makes perfect sense. So depending on the exact pressure, that is going to determine the melting or freezing point. So the temperature here is actually, and the line tells you the melting or freezing point. So let me actually draw a little something for that. So this line represents melting/freezing point. So the temperature at which this will happen based on the pressure. So if you remember the video about Mount Everest, about how the boiling point of water decreases as you go up in elevation because the atmospheric pressure decreases. So that's kind of what it's showing here, that at very, very high pressures, the boiling point or the melting point, well, actually that's the boiling point line, but yeah, at high pressures, the boiling point is lower. At higher pressures, the boiling point is higher. Okay, so that's that section. This section kind of makes sense. At low pressures or high temperatures, you're much more likely to have a gas. So this area under this whole curve, that whole area represents gases. Okay, and this line represents, what would that be? The boiling point. Okay, so like we learned, if you start at a lower altitude, or a lower altitude, you're gonna have a higher pressure, maybe about 1 atmosphere. But as you decrease in altitude and decrease in pressure, the temperature also decreases. So temperature gets lower. That's what this kind of line is indicating. Cool. Okay, the last section is the middle, and this is the liquid phase, of course. Everything in between. This is when water is a liquid. Okay. So every phase diagram is going to be set up essentially the same way. The zones are all the same. The big differences are going to be in exactly what these lines look like. So for example, in different liquids or different substances, maybe this boiling point or this freezing point line might be a different angle, It might start at a different place. It might have a different slope, but it's still the same type of line that describes the same thing. So these are the kinds of questions that you can answer when you look at a phase change diagram like this. So for example, what phase is water at 150 degrees Celsius and 5 atmospheres? So let's see if we can figure out what the answer is. So at 150 degrees Celsius, that's going to be approximately here, and 5 atmospheres. So if we keep going up, that's about 1 atmosphere. We go above it. Well, it's a little uncertain based on this graph, but I would say the chances are it's probably a liquid. So it's pretty hot, but it's under quite a bit of pressure. So chances are it's probably a liquid. That's our answer. Okay, and we can find that because I would bet it's about right there is kind of where we're looking at. Okay. That's one type of question. So if you have the pressure and the temperature in one of these graphs, you should be able to figure out what phase of matter it's in. If that dot were, let's just say maybe we are at 100 degrees Celsius and half an atmosphere of pressure, maybe water would be boiling because the dot would be about here and it's below the boiling point line in the gas section. So it would be a gas. If we were to say, let's say 0 degrees Celsius at, 200 atmospheres of pressure, that might be up here and that might also be a liquid. So it's really just about using this graph and graph interpretation, which you should be able to do. Okay, here's another type of question I can ask you. What is the melting point of water at at 0.5 atmospheres? So this one we are looking on the line. So this is the melting point line. So we want to find 50 degrees, half an atmosphere, which is maybe about here. So we just have to kind of go down and figure out what we think the melting point is. It looks like it's going to be somewhere between 0.00 and 0.01. So kind of here, I'll rewrite that for you. Boiling point is going to be greater than 0.00, but less than 0.01. I don't know what number it's going to be, but it's going to be somewhere in there because of that slope. Now, if we had more information, a better graph, we could probably pinpoint it a little bit more exactly. Yeah, let's see if we can. So that's the plot spot I drew, and it seems to be right in there somewhere. Okay, so phase change diagrams, it's really just that's pretty much as simple as it is. So let's take a quick look at the packet and you can see what we need to do for that. Okay, so here's the packet. This is page 1. Here is a phase change diagram. So all of this is labeled for you. This is not the same as water. You'll notice a couple key features. The biggest feature is that this melting freezing line is the opposite slope. So normally, most liquids, when you exert pressure on them, they become a solid. But water is interesting that when you exert pressure on it, solid water, it becomes a liquid, which is kind of unusual, but it's a cool property of water. Oh gosh. Sorry about the bell there. Okay, so these are all questions. I think I'm going to leave you to answer them and maybe we'll go through them in class together. Here's just some labeling, 3 phases of matter, some really basic stuff here. Just kind of data and graph interpretation. Let's take a look. That's page 1. So I think you guys can handle that one. Here is page 2. Page 2 is more examples. So let me take a quick look and see if there's one of these that looks really good. Okay. So if we were to have a bottle containing compound X in your closet, what would phase it most likely be? Well, your closet is at about 1 atmosphere. So looking at the side of our graph here, the lowest pressure is 10. And degrees Celsius, your closet probably is somewhere between 0 degrees Celsius, which is freezing point, and 100, which is boiling point. So almost certainly this is a gas. Whatever this stuff is, this is absolutely a gas, just if you happen to have it lying around. Okay, so reading like what the units, this is why it's really important to label your axes with units. So we know exactly what we're talking about here. Let's see. At what temperature or pressure will all three phases coexist? So that's going to have to be, it's called the triple point, this little middle point here, where all three of them intersect at once. So that looks like a pressure of about 50 and a temperature of about 350. And you can see it's just reading, interpreting what the question's asking, and then just reading the graph. So finding that temperature and pressure combination. Okay. Number 4 is asking what will happen if you raise the temperature. So what phase, will a phase change occur is basically what they're asking. And yeah, I think you guys can answer some more of these. Those are kind of fun. Let me check a look at page 3 and then we'll decide if we should keep going from there. All right. You're also going to work on pages 3 and 4. It's actually one worksheet. So these are all kind of that same topic. Maybe let's go through this one in a little bit more detail. Okay. Let's see what we got. Conditions necessary for sublimation. You can actually skip this one. These are AP questions, so some of these might be a little tricky. You don't actually know what half these things mean. The actual answer here is conditions for sublimation, but you can just kind of skip this problem. It's a little hard. Latent heat of vaporization and fusion are something we'll cover. Entropy and deviations from the ideal gas law. We're going to learn about the gas law next unit, and deviations from it is also an AP topic. So we'll come back to that later. Let's see. Dense in which is least dense at temperatures immediately below the triple point. Yeah. For this one, these are all multiple choice. I would say technically this thing, yeah, you can skip this one also. I'll just read through these real quick. Yeah. I would say you can skip this one too. It's an A. These are all AP questions. And you can skip 6. We may have to be skipping all of page 3. Let's find out. Sorry, y'all. Okay. Let's say I think you all can definitely, this one you can skip. Let's do this. These are the ones I actually want you to work on. Okay, this is page number 4. And critical temperature, which of the following statements are true? Yeah, why don't we skip these? Okay, so it turns out 3 and 4 were a little overly ambitious, maybe. Okay, so from 4, why don't you just work on this one? And again, I think it's something we can go over in class. So you can actually pretty much skip most of page 3. Oh, I thought I had muted. I did not mute. You had to hear the bell. Sorry about that. Okay, so let's do this. Let's skip page 3 and 4. Don't worry about those, or definitely page 3. And maybe just look at page 4. You know what? Let's go over this one together, and then you can go back and do the others. Okay. So, these are our word bank that we can add in here. If the temperature increases from 100 Kelvin to 200 Kelvin at 1 atmosphere, which of the processes occur? So let's start at 1 atmosphere is here. So we're going from 100 K, which is going to be about here, to 200 K, which is about here. So what's going to happen? Well, it looks like we are going from a solid to a gas. So that's going to be sublimation. Okay. If the temperature decreases at 6 atmospheres, which is about here, decreases from 300 K, which is approximately here, to 220, which is probably just about here. So this direction, what is happening? It looks like we're going from a gas to a liquid, so that's going to be condensation. And then finally, if the pressure increases from 6 atmospheres to 70 at 220K. Okay, so 220K is here. We're starting at about 6, which we agreed was here, up to 70, which is like maybe right about here, something like that. It looks like maybe we're going from a liquid to a solid. That maybe 70 is right about here, just over the line. So that looks like freezing to me. All right. So anyways, that's kind of how you do this. So we'll stop there. Yeah, we'll switch this. You're just going to have to work on pages 1 and 2. So that cuts back the amount of work, which is great. And next time we will work on density. Excellent.